What is the main contribution of the proposed method, fungi?
The main contribution of the proposed method fungi is that it combines neural network features and gradients to enhance representations for the k-nearest neighbor algorithm. Fungi extracts gradients from self-supervised loss functions, projects them to smaller dimensions, and concatenates them with neural network embeddings. This method allows for the incorporation of a diverse set of pre-training objectives, such as contrastive learning and self-distillation, to improve downstream performance without the need for training or feature engineering. Fungi can be seen as a non-parametric transfer learning approach that enhances the neural network's embeddings with gradient information specific to the downstream data, without requiring any parameter updates. The method consistently achieves performance improvements across multiple models and benchmarks, including image, text, and audio classification tasks, as well as in context image segmentation and image retrieval tasks, utilizing a total of 16 backbones.
How does the proposed method fungi enhance the k-nearest neighbor algorithm?
The proposed method fungi enhances the k-nearest neighbor algorithm by incorporating features from unsupervised gradients obtained from self-supervised loss functions. These gradients are extracted from pre-trained backbones and concatenated with neural network embeddings, providing additional information cues from data without the need for training or feature engineering. The fungi features are obtained by normalizing the gradients and embeddings, concatenating them, and reducing their dimensionality via PCA. This process allows for the combination of multiple losses at ISO storage cost, improving the representations for the k-nearest neighbor algorithm. The method leverages gradients from various self-supervised objectives like DINO, SIM-CLR, and KL divergence, integrating complementary information that enhances the model embeddings. By combining these gradients with embeddings, fungi acts as a non-parametric transfer learning approach, encoding first-order learning signals specific to the downstream data without requiring parameter updates. The method consistently improves performance across multiple models and benchmarks, demonstrating its effectiveness in enhancing the k-nearest neighbor algorithm for various tasks such as image, text, and audio classification, as well as in context image segmentation and retrieval tasks.
What are the theoretical benefits of incorporating fungi in the k-nearest neighbor algorithm?
The theoretical benefits of incorporating fungi in the k-nearest neighbor algorithm lie in enhancing the neural network's embeddings by incorporating features from unsupervised gradients. Fungi, obtained from self-supervised loss functions, do not require human annotations, allowing for a simple enhancement to embedding only KNN. These gradients are projected to smaller dimensions and concatenated with the neural network embeddings, providing new inputs to the classic KNN algorithm. By combining these gradients with embeddings, fungi can be seen as a non-parametric transfer learning approach, where the gradient information encodes first-order learning signals specific to the downstream data without needing to update any parameters. This approach offers consistent performance improvements across multiple models and benchmarks, demonstrating the predictive abilities and complementary information that the gradients from self-supervised losses can provide to model embeddings.
How are gradients obtained and utilized in the fungi method?
Gradients in the fungi method are obtained from self-supervised loss functions, specifically from the self-attention output projection of the last transformer block. These gradients are extracted without the need for human annotations, making the process unsupervised. The fungi method incorporates these gradients by projecting them to smaller dimensions and then concatenating them with the neural network embeddings. This combination of gradients and embeddings enhances the representations used in the k-nearest neighbor algorithm. The gradients are derived from various self-supervised learning objectives such as DINO, SIM-CLR, and a KL divergence-based loss. By integrating these gradients with the neural network embeddings, fungi improves the predictive abilities and offers complementary information to the model embeddings. The method ensures that the gradients encode first-order learning signals specific to the downstream data, without the need to update any parameters, making it a non-parametric transfer learning approach.
What experimental results were achieved with fungi across different benchmarks and tasks?
Experimental results achieved with fungi across different benchmarks and tasks include consistent performance improvements across 11 image, 5 text, and 2 audio classification benchmarks, as well as 2 in-context image segmentation and 2 image retrieval tasks. Fungi demonstrated significant enhancements in k-nearest neighbor (KNN) classification for various VIT backbones with different model sizes and pre-training strategies, achieving consistent gains regardless of the model used. In low data scenarios, fungi showed a significant improvement when 3 to 6 shots were used, highlighting its potential in data-efficient settings. Additionally, fungi significantly enhance the performance of Dino VIT-S16 and VIT-B16 models in retrieval-based semantic segmentation tasks on Pascal VOC 2012 and ADE20K datasets, producing sharper and more complete segmentation masks. Notably, fungi improved Dino's performance across all memory bank sizes, with the most substantial enhancements observed in smaller memory banks for VOC. Overall, fungi consistently provided performance improvements across various benchmarks and tasks, showcasing its effectiveness in enhancing representations for the k-nearest neighbor algorithm.
What are the considerations and findings regarding the choice of layer for extracting gradients in the fungi method?
The considerations and findings regarding the choice of layer for extracting gradients in the fungi method are based on the predictive features provided by different layers of the neural network. The paper extracts gradients from the self-attention output projection of the last transformer block. Deeper layers are chosen because they are expected to provide more predictive features. The results confirm this assumption, showing that deeper layers consistently produce more predictive gradients across all losses. For shallower blocks, the second MLP layer is significantly more predictive, but as the blocks become deeper, the performance gap between layers becomes insignificant. However, the attention output projection layer is favored slightly for deeper blocks due to its efficiency in terms of memory usage, as it utilizes fewer parameters compared to other layers.